All right, so the goal of this chapter is to be able to take a given function, has some formula, and find the area between that function, the x-axis, and two vertical lines, x equals a to x equals b. So here is a picture of some random function, and I want to find the area. Here, this is the x-axis. Between my curve, the x-axis, and two vertical lines. So this area is the goal. I want to be able to find the area under a curve. Okay. So there are some surprising applications of being able to find the area under a curve. In the last class, we saw that the area under a velocity curve gives what? Displacement. Yep. Or distance, depending on how you use the information. But we're going to get to those applications later in Calculus 2. For now, we're just going to focus on the problem of finding the area under a curve. Technically, how do we do it? So, also in the last class, we estimated area under a curve by using rectangles, like in this picture at the right. So, I broke my interval a to b up into n pieces, and then in this picture, am I using left endpoints or right endpoints to get the height of the rectangles? Right, yeah. So in this first interval, a to this other endpoint here, I am getting the height of the rectangle by using the height of the curve at the right endpoint. Right. So I could use right endpoints or left endpoints. There are also other things you could do. You could use the midpoint. For right now, we're just using left and right endpoints. So how do we get a better estimate for the area under the curve? Here's a picture where, well, in all of these pictures, I'm using midpoint to get the height of the rectangle. But to get a better and better estimate, use smaller and smaller rectangles, right? More and more intervals. And so here you could say we're letting the number of rectangles go to infinity, or the width of each rectangle go to 0. So we're taking a limit. Right? To find the exact area under the curve, we estimate it with rectangles. We let the number of rectangles go to infinity, and that's a limit. That's what makes this a calculus problem. We have to take a limit to find the exact area. Okay, so we're going to take a quick detour. This is all just notation. Okay, so it's just a handy way to write sums if you have a long list of numbers, right? So for example, if I want to add 5 plus 10 plus 15 plus 20 plus 25 plus 30 plus 35 plus 40 plus 45 plus 50, well, you might say, well, every number in this list is a multiple of 5. And you'd say, okay, so I'm adding multiples of 5, so that's where this 5k comes from. 5 times something makes a multiple of 5. And we're saying, okay, let k go from 1, because 5 times 1 is 5, and that will give me my first value in the sum, to 10. And you put the 10 at the top because 5 times 10 is 50, and that gives me the last number in the series. Okay, so this big capital E is a summation sign. Okay, so that is universally used throughout math to mean the sum. Okay, so we could use sigma notation to write this series as the sum from k equals 1 to 10 of 5k. The k equals 1 and 10, those are called the limits. Don't confuse them with calculus limits. It's just the limits of what I plug in. The index is, k is called the index, and the 5k is called the summand. So your calculator can find sums pretty easily if you want it to calculate a sum for you, but we're going to skip this, but you can read it if you want on your own. All right, so in the last class, we saw this messy formula for a right-hand sum, right? And it was just adding up areas of rectangles. Each of these terms in this sum is the width of a rectangle times the height of a rectangle, right? Delta t times f of t1. So this was my picture, and I'm finding a right-hand sum. So I look at my first interval here from t0 to t1, and I'm going to use the right-hand endpoint, the t1, to determine the height of the rectangle. So I go to t1, I go up to the height of the function, and that's the height of my rectangle on that interval. And then this width is delta t, which we said we calculate by doing b minus a over n. And then the height of this rectangle is f of t1. So this is called a Riemann sum. When you do this right-hand, left-hand endpoint thing, it's called a Riemann sum. And we can use sigma notation to abbreviate it. So we would say distance is approximately equal to the sum from k equals 1 to n. So I'm using 1 and n as my limits here. And these terms all look like delta t times f of t sub k. And then what do we do again to get better and better approximations of the exact area under the curve? Make n larger. Take the limit as n goes to infinity. So it turns out that, in fact, total distance exactly is the limit as n goes to infinity of the sum from k equals 1 to n of delta t times f of t sub k. That is a full-fledged, no messing around definition for the area under the curve. It's the limit as you let the number of rectangles go to infinity of the right-hand sum. Or the left-hand sum, we're just doing the right-hand sum because you don't have to do both. They both give you the exact area. And sorry, for the limits, for the index, I used I when I wrote this. You could use K or J. Those are the most common letters used for indices. All right, so this formula is not something you need to memorize, but calculating under a curve, area under a curve, is something we're going to do many times. So we're going to use some new notation to avoid having to write this formula down all the time. Right? We're going to invent some new notation that just means this. Take rectangles, let the number of rectangles go to infinity. All right, so this new notation is super important in any future calculus classes you take. We are going to let this definition of the exact area under the curve, which is the limit of the sum of the rectangles as the number of rectangles goes to infinity, we are going to write that like this. So this symbol means sum, right? So the way I sort of interpret how this notation changed into this notation is I said, okay, well, that means a sum, and this is like a long S, right? So I got rid of the limit. So it's like I took that short sum and I elongated it because I'm using lots of rectangles. And then this notation never told us what the endpoints were, A and B. You have to already have a picture and already know what they are. Here we have A and B are the endpoints of where I'm trying to find the area between. Those are the x values that I'm trying to find the area between. And then f of t is my function. So instead of doing f of t sub I just write f of t when I take the limit. And instead of delta t in the limit, that becomes a dt, right? Because as the number of rectangles goes to infinity, that width, delta t, goes to 0, and we call it dt in the limit. Same as when we were first calculating slope of a tangent line. You know, when you find slope of a tangent line, we did delta y over delta x to approximate it, and when we took the limit, changed to dy over dx. All right, so this symbol, this long S with an A and a B with some stuff inside, dt, is called a definite integral. The numbers on the integral sign are called the limits of integration. Again, not to be confused with limits that we've been calculating all year. And the function is called the integrand. Or integrand. So actually finding areas using the formula where you have to use the limit definition of the definite integral is tough. Remember back when we first learned derivative and we had to calculate derivatives using the limit definition of the derivative, and that was tough? This is way tougher. But it's the same kind of idea. So your calculator, though, can do a pretty decent job of estimating this. Get you pretty close to an exact answer. So the integral from 0 to 3 of x squared dx, that means the area under the curve y equals x squared from 0 to 3. So let's have the calculator find this area for us. Okay, so my favorite way to do it is to put the integrand in y1. So I'm going to type x squared into y1. I got to choose a good window, so I'm mostly interested in 0 to 3. So maybe I'll go like -1 to 4, and then my y will go -1 to 20. Oops. So I'm just going to graph it. And I say, okay, so I'm looking for the area from between 0 and 3 that's under this curve. So just this area right in here. All right, so my calculator can estimate that area for me. You go into the calculate menu and you choose option 7, which is an S, that integral symbol of f of x dx. So we hit that. And then it just asks you for the lower limit, which for us is 0. Enter. And the upper limit, which is 3 for this problem. Enter. And it shades the area and tells you how much area there is. So the area under that curve appears to be 9. All right, so you can also do it in the home screen without a graph. The advantage of that is that you don't have to choose a window first. The advantage of this is that you get a visual of what that integral calculation is actually calculating. But we could also do it just in the home screen. Go to the math menu and you choose fint for integral, function integral, fn int. All right, and then we type in the function, which you could either just type x squared or you could put in y1. I'll do x squared, it's a little quicker. Okay, and then you do comma x, you're just telling it that x is the variable, and then the lower limit, then the upper limit. And it'll give you 9. So 2 ways to find it. All right, and then last class we talked about what happens if the function is negative. This rectangle would be delta x, right? The width of it would be delta x, but its height of it would be negative, right? The function value would be negative. So all the rectangles that lie under the x-axis are going to contribute negative area to the total. Okay, so when you take an integral, it is it's a net, right? It's a signed area where stuff above the x-axis has positive area and stuff below the x-axis has negative area. All right, so if I want to find the area between the curve y equals x cubed and the x-axis from -3 to 0, that means take the integral from -3 to 0 of x cubed dx. Right? And just try to keep in mind what this notation means. This is saying we're going to add up a bunch of rectangles that have a height of x cubed and a width of delta x. And we're going to take the limit as the number of rectangles goes to infinity. So it's very easy to forget when you get into specific techniques why you write this dx there, because we often don't do anything with it, but it is important notation. All right, so let's see. X cubed looks like that. And I'm trying to find the area from -3 to 0. So this is the area I'm looking for. So when they ask for the area, that's a positive value. When I take the integral from -3 to 0 of x cubed, it's on my calculator, it's going to give me a negative answer because all of that area is below the x-axis. So let's just have the calculator do this quickly. Int of x cubed, comma x, comma -3, comma 0. And we come up with -20.25. Which means that the area that they asked me about is 20.25. Does that make sense? So you do have to pay attention to what question they're asking you in terms of when to use the signed area and when to take an absolute value. All right, same function. This time I want to find the area between -1 and 2. Draw a picture of it again. Okay, so I'm looking for that area. I'm going to do it in 2 ways. I'm just going to do something a little tricky, right? So what ideas do you guys have? If you want to find that total shaded area. Yeah. So these 2 guys have the exact same area. One's positive and one's negative. Right? And then so I could just take the integral from 1 to 2. $3.75. But then we have to be careful, right? Find the area between the curve and the x-axis. Do they mean all the area or the signed area? It's not super clear. Let's find that area. That area would be the integral from -1 to 0. Which is -1/4. Right. And then the area from 0 to 1 is also 1/4. Right. So if I had taken the integral from -1 to 1, it would have told me 0. But if I want to know the total area, I'm going to have to go -1 to 0 and double it, or absolute value and double it. So my total area is going to be 3.75 plus a quarter plus a quarter. So 4 1/4. So that's my total area. My net area, right, if I think about the signed values, would be just the 3.75. Okay, you try this one. All right, we'll just do it together quickly. I want the integral from -2 to 2 of e to the x minus 5x, and I have a graph here already drawn, so I'm looking for the signed area between -2 and 2. So I already know that my answer to this integral should be positive or negative. Positive. There seems to be more positive area than negative area for when I do the net. Okay, so my preference is the visual one. You can also just do it in the home screen, but I like to see the area shaded. E to the x minus 5x. And then zoom 6 looks good. And calculate the integral from -2 to 2. 7.25 approximately. Good. All right, so to summarize, what we have discovered is that when you have a velocity time graph, the area underneath is distance traveled. There are other applications that we will learn about later. But to find that area under a graph, one method we can use is to make rectangles that approximate the area. And then to get the exact area, use more and more rectangles. Let the number of rectangles go to infinity. And your calculator can do a really good job of approximating the area under the curve using the integral command. All right, so let's jump right into the class 39. Okay, so I want to be able to reconstruct the value of a function from its derivative. So if f of t represents the value of a stock market investment t months after January of this year, and I know that on the first day of the year, the value of this investment was $100. F of 0 is 100. All right, so then f prime of t represents the rate of change of the value in the investment, and what are its units? Dollars per month. Yeah. So remember, derivative units are y units over x units, right? Because a derivative is the slope of a tangent line, and the tangent line is change in y over change in x. So it's y units over x units. And in this case, that's going to be dollars per month. Okay, so f prime of t represents the rate of change of the value in the investment in dollars per month. And here I have it graphed, the derivative function. All right, what can we say about the value of the investment at the end of the month? Well, I know f of 0 was 100, right? So there's my starting point. And then in month 1, what's my rate of change? $20 per month. So I started $100. Well, sorry, at month 0, I should say, at month 0, my rate of change was $20 per month. So I started at $100, and my value was changing by $20 per month positively. So what should my investment be worth at the end of month one? $120. And then in month one, my investment continues to have a rate of change of $20 per month. So that means that by the time I hit month two, my investment should be worth $140. In month two, my investment is changing by $20 per month. So by the time I hit month three, I should have $160. And in month three, what's the rate of change of my investment? $10 per month. So by the time I hit month four, my investment should be worth $170, another $10. And then in month four, what's the rate of change of my investment? $0 per month, which means that in month five, I still have $170. Didn't change. All right, in month five, what's the rate of change of my investment? Negative $20 per month. So by the time I hit month six, how many dollars am I going to have? $150. And then in month six, my rate of change is negative 40. So in month seven, I'll have $110. Okay, so at time zero, start with $100. All right, and then I look what happens over the entire first month. I don't want to look at the rate of change just at time zero, but what's happening over my entire month one. Well, 1 month has passed, and my rate of change was $20 per month. So this rectangle represents 1 month times $20 per month, which is a change of $20. Right? So this was correct. This is 120. Okay, and then we're going to look at what happens in the second month. From month t equals 1 to t equals 2, 1 month has passed, and we have had a constant rate of change of $20 per month. So this rectangle is $20 per month times 1 month, $20. So this is also 140. But then from month 2 to month 3, my rate of change wasn't constant, right? So well, the last time we just did this, I was assuming a constant rate of change of 20, but that wasn't right. But I can find the exact area, right? Because this is just a trapezoid, right? Or I could find an overestimate and an underestimate and average them, right? But I can find the exact area. So this is 20, 20. This little guy is 10. And what's the area of that little triangle? 5. So that's a change of $15 in that month. So from over month 2 to month 3, t equals 2 to t equals 3, we had a change in value of $15. So this is 155. All right, and then from month 3 to month 4, I could assume that I was at a rate of change of $10 per month the whole time, or $0 per month the whole time, but one would be an overestimate, one would be an underestimate. The exact value of the change would be the area under this curve, which is 5. So I have an increase in $5 to 160. All right, and then I go to my negative area. Right now my rate of change is negative, which means the value of my account is going to be decreasing. So from t equals 4 to t equals 5, that's 1 month. And this area represents the change in value of my account. And what is that area? $10, yeah. So this is a triangle with a base of 1 and a height of 20. 1/2 1 times 20 is 10. Okay, so my value decreased by $10 here, so it goes to 150. All right, then from month 5 to month 6, this area represents the change in value of my account. So I can break this into pieces I can find the area of. This is 20 and this is 10, so that's a loss of $30. So I'm now at 120. And then from month 6 to month 7, I have a constant rate of change, so I can just multiply rate times time, get total change. 1 month times negative 40 is a loss of $40, so I'm at $80. All right, so the area between the derivative and the t-axis represents the change in value of the investment over the course of 7 months. So we could represent this area with a definite integral, the integral from 0 to 7 of f prime of t dt. And we could also represent the change in value of the investment by taking the value at month 7 minus the value at month 0. So I have 2 ways to calculate total change in my investment. I can take a definite integral of the derivative function, or I can just use the original function, plug in times 7 and times 0 and subtract them. So putting it together, we have that these 2 things are equal. 2 ways of calculating the same value. This is true in general, and it's very important. It's called the fundamental theorem of calculus. If f prime is continuous on some interval, then the integral from a to b of f prime of t dt is f of b minus f of a. In English, this says that the definite integral of a rate of change is total change. The definite integral of a rate of change is total change. The definite integral of a rate of change is total change. Everybody got it? Okay. This is kind of like the derivative is the slope of a tangent line. The derivative is the slope of a tangent line. The definite integral of a rate of change is total change. All right, so for example, if pi prime of x is marginal profit, so marginal profit is the rate of change of your profit, right? Measured in dollars per unit. So how many more dollars do you make for each additional unit you produce? Or how many dollars do you lose for each additional unit you produce? From selling X units of a product, then the integral from a to b of pi prime of x dx, according to the fundamental theorem, is going to be pi of b minus pi of a. And it represents the change in profit, right? It represents the difference in the profit when you make B units versus when you make A units, right? How much more or less profit results from B units than A units. Okay, so here is the reason that we write the dt, right? This is important. So the units for the integral from a to b of f prime of d dt are the product of the units for f prime and for t, right? Because this is, think of this like a product, f prime of t dt. These have y units per t units times the units on dt are t, and those would cancel. So the integral has units that are just y units, right? The product of the t units and the f prime units are just the y units. So if we go back to this original investment example that I did, when I was calculating these rates of change, these amounts of change, let's say, for example, this last rectangle here, that 40, I calculated its units by taking my 1 month versus negative $40 per month, right? And I multiplied 1 month times negative $40 per month. Months cancel, and we get a loss of $40. So these are F prime units times time units gives you Y units, your original Y units. All right, so a honeybee starts with 100 bees and it increases at a rate of n prime bees per week. And T is measured in weeks. What does 100 plus the definite integral from 0 to 15 of n prime of T dt represent? Close. Number of bees at what week? Week 15. Yeah. So 100 is my original number of bees, right? That's why that's there. And then this guy is my integral from 0 to 15. That represents the total change in my bee population from week 0 to week 15. So this is growth or decay, right, depending on what's happening, of bee population. How much it has grown or shrunk by. So this final thing represents total bees in week 15. All right, so here's another one. The rate of flow of oil through a pipe is given by this derivative function because this is a rate. So we're going to call it a derivative, f prime, measured in gallons per minute at time t. Find the amount of oil passing through the pipe in the first 20 minutes. Discuss in your groups. Come up with a strategy. All right, so pretty much most people have a good setup for this. So if we know the rate of change, right, we can find the total change by just taking the integral, right? The integral of a rate of change is total change. So they're asking me for total change, how much oil has passed through this pipe, and I know the rate of change of the oil. So my total change is going to be the integral from 0 to 20 of f prime of t dt. And my units will be my f prime units, which is gallons per minute, times my time units, minutes. So this should come out in gallons. So I'm going to have my calculator do the actual integral because we don't have any techniques for that yet. And I think I'm probably going to do it in the home screen because I have no idea what a good window will be for this. So I go math, fint, and I type in the function. So it's going to be x times 2 plus sine x. And then divided by 3 plus x, comma x, comma 0, comma 20. I think I got the parentheses right there. We will see. $27.55. Other people got that? Okay, good. Okay, suppose we know R prime. We know a formula for the rate of change of the population of a city at time t in years since 1990. Can we use this information to find the population in the year 2000? The size of the population in the year 2000. Right. We don't know the initial population. We can find out how much the population has grown or shrunk. Right. I could take the integral, right, 0 to 10, because we're going 1990 to 2000, of R prime of t, right? But that's going to tell me the change in the population size, right? I would need to know what it started at to find out what it finished at. This just tells me how much it grew or how much it shrunk. So basically, no, can't find it. All right, one more application of integrals. So this would be to find the average value of a function. So we're about to derive a formula for average value. Formula is easy to use, and that's all I need you to be able to do with it, right? But if you're able to follow what we do in this derivation, the formula will have more meaning to you. Ready? Let's go. Okay. So the goal is to find the average y value of infinitely many y values over an interval. Right? So here's my interval from A to B. There are y values all along this interval. So imagine if I could take all of them, add them up, and divide by the number of points. That would give me an average y value. So, but the problem is there are infinitely many, so this is a little bit tricky, right? Can't just add them all up and divide by the number. So instead, I'm going to chop the interval a to b into n equal pieces, just like I did when I was doing integrals or rectangles. And I'm going to evaluate the function just at these specific points. So I'm just going to say, okay, well, I can get a y value here, and here, and here, and here, and here, and here. So I just pick a few y values along the curve, add them up, right? So these are just my y values at each of the interval endpoints. Add up all those y values and divide by n. Or add them all up and multiply by 1 over n. Same thing. Okay, but remember that delta t, which is just the width of each of these little intervals here, delta t, is b minus a over n. So do a little manipulation with that, right? Delta t is b minus a over n. Just divide both sides of this equation by b minus a. So on the right, you just are left with 1 over n, and on the left, you have delta t over b minus a. So then I can replace 1 over n with delta t over b minus a. Okay, so my big conclusion, when I put in a delta t over b minus a there, I can leave myself enough room to write this. So instead of 1 over n, I have delta t, and instead of over b minus a, I'm going to write it as 1 over b minus a times delta t times f of t1 plus f of t2, f of tn. Okay, now this is a formula, should look familiar. What is that? If you distribute the delta t. Those are the areas of rectangles. Yeah. This is the right-hand Riemann sum. Okay, so if I let the number of rectangles go to infinity, that guy that I circled in blue there is just the integral from a to b of f of t dt. So the average value of a function on an interval a to b is 1 over b minus a times the integral from a to b. of the function. All right, so one quick example where we'll use this formula. The value of a Tiffany lamp T years after 1965 is given by this exponential function. So the value is increasing by 15% per year. So what's the average value of the lamp over the years from 1965 to 2000? So average value of a function is just 1 over b minus a times the integral from a to b. And now I just plug in the stuff, right? So this is going to go from 0 to 35. Yep. So this is 1 over 35 minus 0, if we're counting 1965 as year 0, times the integral from 0 to 35 of this function, 225 times 1.15 to the t dt. Right, it doesn't have to be, right? To find average value of a function, you use the function itself when you do the integral, yeah. Because we're not looking for total change. It's a different application. All right, so math 9. 225 times 1.15 to the x, comma 0, comma 35. And then I'm going to take that value and divide it by 35 years. $6,079 is the average value of the lamp over the 35 years. 6,079. 62. So let's just think about whether or not that makes sense. What was the value of the lamp at time 0? 225. Just plug 0 into the value function, you get 225. Let's figure out the value of the lamp at time 35. So if I let $225 grow exponentially at 15% for 35 years, the final value of the lamp is almost $30,000 at the end of the 35 years. So if this value function is really true, then an average value should come out somewhere between, the starting value of 225 and the finishing value of 30,000. So that would make sense. This may or may not be a good function to model the value of a Tiffany lamp. All right, I think that's a good place to stop.